VerifLLMBench, an open source benchmark for test benches generated with large language models. This is the University and Synopsys Corporation. The listen to capability of generating RTL designs from a natural language provide a possible glimpse into future design and coding. Benchmarking used in the context of generative design verification offers a method to evaluate the effectiveness of a generator. A benchmark, especially one that is open source, well-known and maintained, is a crucial part of the generative process. Previous work has explored the generation of the RTL design from natural language description. One paper seeks to extend this work by providing a benchmark and a methodology to evaluate the effectiveness of UVM test bench generation. We presented the structural methodology for a benchmarking UVM test bench generation from the natural language using state-of-the-art LLMs. Our approach is to incorporate verified DUTs and LLM-based UVM test bench generation, iterative refinement of a prompt to resolve syntax errors, and thorough the coverage analysis. The integration of the UVM linting ensures that the linear generated test bench meet industry standard, providing a solid framework to evaluate the quality and the reliability of the LLM-driven verification code. We evaluate the LLM performance based on the build success rate, coverage metrics, and the linked errors and warnings. Although the design used to the demonstration coverage metrics are relatively simple, we demonstrated challenges and gaps encountered by LLMs and in generating the robust UVM test benches that provide a high functional coverage. The benchmarking results highlight the key limitation of the LLM-generated UVM test benches, emphasizing the need for a refined methodology and advanced training to enhance the coverage, adaptability, and reliability and verification environment. Future advancements in LLMs, including those large context windows and the UVM-specific training, will hold the significant potential to bridge these gaps and drive more robust and reliable generative solutions for design and verification. In this comes the LLM, Large Language Models, Universal Verification Methodology, UVM, and System Value, and Design and Testing, and the Testbenches and Benchmarking. Chapter 1, Introduction. Automated RTL generation based on the natural language prompt has become feasible in the recent years, and some recent works have focused on the use of the large language models, LLMs, and to generate RTL designs, and the verification of such design search required the generation of a test bench TB that evaluates the quality of the generated RTL. Building upon the foundation of the previous work on the RTL generation, this paper leverages the LLMs to synthesize the UVM TBs and introduce a benchmarking methodology to evaluate their effectiveness. The proposed approach enables a multi-dimensional quality assessment of the generated TBs, allowing the systematic comparison for different verification generators. Our work is motivated by first reference, which explored the use of the LLMs to generate RTL. The authors of the two supplemented their RTL description with handwriting implementation and system value, as well as simple and natural manually written TBs to verify them. Generative tools were used to assess the quality of the SB designs generated. The paper presents the UVM benchmark that can be used to compare generative method in a consistent way. Our work provides a benchmark suited under MIT license, promoting a standard for evaluating generated UVM TBs. In both 1 and 2, the primary goal was to create a series of natural language description with the objective of generating RTLs for various designs using LLM. The goal of our work is to extend this concept to address the needs of verification engineers who need a benchmark to evaluate the effectiveness of tools to generate the UVM verification code. Chapter 2, Background. UVM, Universal Verification Methodology, UVM. UVM offers a structured and reusable approach to design specific through the constrained random testing and coverage-driven method, although it requires significant setup and expertise. In contrast, the former verification provides exhaustive and mathematically rigorous checks to provide property across all scenarios especially they found in the corner cases facing scalability issues with a large design and unit testing, while simple and effective for early verification of the individual modules, lack the coverage that's needed for the full system interaction test. A balanced verification strategy often combines the UVM's comprehensive capabilities, a formal method for critical properties, and unit tests for early-stage validation. This work focuses on using the LLMs to generate benchmarks to UVM test bench and for HDL designs. B. Large language models. The section of the LLM for the generating of the UVM test benches is based on optimizing the relevance of the training data, the efficiency of the parameters to computational feasibility, and the cost effectiveness. A model that aligns well across these dimensions offers a strategic advance and enabling high quality and standard aligned TV generation that supports robust HDL design verification. We consider the following LLMs. 1. ChatGPT 4o only is optimized for conversational and multimodal tasks and offers fast response times and a high versatility in both generation purpose and programming context. It leverages OpenAI's proprietary dataset with a strong performance across a wide range of language tasks. The Gamma 2 is an open source LLM developed by Google, at least the largest, with 27 billion parameters. It delivers benchmarks of performance that exceed the models more than twice its size. Gemini 1.5 Pro is part of the new generation of the multimodal models that integrate sparse and dense scaling alongside significant advance in training, distillation, and serving the infrastructure that allows the model to excel in efficiency, reasoning, and planning, multilingual capabilities, functional calling, and long context performance. Llama 3.1 is a highly parameterized transform that developed by the Meta. It is used primarily in academic and industrial research setting and is known for the customizable quantization. Llama 3.2 is the latest model from the Meta offering the advanced imaging reasoning, multilingual text generation, and tool calling capabilities, and with larger models excelling in visual linguistic tasks and small models enabling private application on device. The comparison of various LLMs is shown in Table 1. Table 1 is comparison of LLMs. The choosing an LLM for a task generating UVM test bench for HDL designed depending on several metrics as outlined below. 1. Licensing. Licensing plays a role in the selection of an LLM. Open source models such as Google and Gamma, Meta, Llama 3.2 and Llama 3.1 provide greater flexibility for customization and fine-tuning with permissive licenses that can be suitable for both commercial and non-commercial purposes. However, the proprietary models such as OpenAI's ChatGPT-4o or Google's Gemini 1.5 Pro often comes with stricter usage terms and a higher cost, which might restrict deployment in sensitive or resource-constrained settings. When choosing an LLM, it's important to align the licensing terms with the project budget, the scope of usage, and a compliance requirement. Number of parameters. Number of parameters is the primary determinant of the LLM's ability to capture intricate patterns in language, directly impact the effectiveness of the general complex and structural output. For UVM test bench, a model with a substantial parameters count can provide the depth needed to the interpreted and nuanced verification environment requirements, improving its capacity to generate details and contextually accurate test benches. However, while the higher parameters count generally yield greater precision, they also increase computational demands and necessitating a balance between model complexity and operational efficiency to ensure responsiveness and practicalities. 3. Context windows. Context window determines how much information the model can process and remember within the single query or session. For UVM test bench generation, a longer text window is critical to handle large HDL designs and intricate verification requirements without losing the currency or omitting the crucial details. Models with a long context window, such as Google industry-leading 1 million token They can maintain the continuity across the complex interaction, allowing them to process detailed specifications and produce comprehensive test benches. However, longer context windows may also be substantial, sub, susceptible to errors in a generative UVM test bench, such as logical inconsistencies or misinterpretation of requirements, necessitating a balance between input length and success rate. For compute power, the computational requirement of a model impact both inference time and impulsiveness, particularly for resource-intensive LLMs with a high primary count, directly affecting the feasibility of real-time and iterative table generation. For large-scale or continuous verification need, computing the efficiency is paramount to maintain productivity while managing resource costs. In addition, the fine-tuning open-source LLMs for UVM-specific tasks can further amplify the computational demands, highlighting the need to match a model requirement with available hardware resources. For a given LLM having a primary count P and quantization mode Q, 4-bit, 8-bit, 16-bit, 32-bit, the amount of the GPU memory M required to load the model given by the M, P multiply 4 bytes over 32 over Q and then multiply 1.2 over 10 power 9. The where 1.2 accounts of the 20% overhead for common use cases of auxiliary operations, buffers and inefficiencies, and countered during training and inference. Table 2 shows the memory requirement for open source LLMs and is followed by the example of GPUs that can run one of the models. The table 2 is GPU memory requirement in gigabyte models quantizations. The example of GPUs can run in the Llama 3.1, 405 billion parameters, 5x AMD MI300 192 gigabyte GPUs in a 16-bit mode, 8 times NVIDIA 800 and 880 gigabyte GPUs in 8-bit mode, 4 times NVIDIA 880 gigabyte GPUs in 4-bit mode. For cost consideration encompasses both licensing expenses and operational cost for compute resources. High-performance LLMs with extensive training often come with substantial licensing fees, which hardware cost to large models add further financial implications. Balancing cost is the projected efficiency gains of the model, such as reduced time to generate and debug TVs or higher verification quality, chosen from the assessment of the return on investment for frequent UVM test bench generation. C. Prompt engineering. Prompt engineering plays a crucial role in LLM performance optimization. Specifically, it focuses on crafting structures prompted to guide LLMs in creating correct, reusable UVM verification component. UVM relies on a modular component like its agent, driver, sequences, and etc. Prompt engineering enables LLMs to generate these components effectively by embedding DVM specific terminology, structure, and best practices into a prompt, ensuring the generated code adheres to UVM complex stacks, encouraging the modularity and configurability, and aligning with the verification needs for scalability and reusability. We use prompt retirement in this work where an initial prompt is submitted to an LLM and successive adjustments are made through the prompt based on the LLM's responses until a satisfactory output is achieved. This approach can iteratively improve the quality and accuracy of the responses, although it requires additional human interaction and iterative feedback loop is used. Using the model outputs as a feedback, subsequent prompted LLMs are designed to correct errors or improve the clarity of format, and the cycle continues until the output meets the required statement, such as being free from text errors and complying with the desired format or the content requirement. 3 is methodology. The benchmarking. Chapter 3 is methodology. Benchmarking, design and benchmarking, TB take different approaches. To benchmark the design, the output responses from a given input stimulus must be compared against the expected output, a common check performed by the verification engineers. However, benchmarking a TB is a less familiar and more challenging ideology. It does involve evaluating the quality of the stimulus and its ability to exercise the functionality of the design under test DUT. This task is not straightforward in part. This is not straightforward in part because it involves proposing a solution to the recursive task of testing the tester. A. The experimental setup. To ensure the consistency of the emphasizing the implementation of a UVM testbench component, a uniform starting point is provided on all LLM runs. Defining the interface and top-level modules in advance addresses several challenges. LLM has a limitation in managing the extensive context, speaking the implementation of this component allows more context capacity to generate and define the UVM test bench, which is the primary focus of this work. Now, by narrowing the scope of the UVM class TB code, we enable direct comparison of the TB generated by the different LLMs. Without a standardized top-level module and a DUT interface, variations would complicate the functional coverage analysis. Hence, the stable predefined TB harness provide a reliable foundation for consistent performance evaluation. We begin with the synthesized verified RTL model. One is that is the DUT as shown in the figure 1. The DUT is a verified RTL design taken directly from the reference 1, beginning with verified design enables us to isolate the potential issues within the test bench generator. An interface is created consisting of all outputs of the DUT. System value cover groups and cover function, including the facilitated coverage analysis. We consider the 5 DUTs with verified complexity and design features. For each design of wrapper, an LLM-TV component, and a coverage-enabled interface were created. One is accumulated 8-bit data and output after 4 inputs. 2. Adder 8-bit and an adder 8-bit adder. Adder 16-bit and an 16-bit adder implemented with the full adders. 4. FSM sequence detection circuit. ALU, an ALU for the 32 bits as a CPU. Figure 1 is the LLM TV generation to build the flow. The top module instantiated a DUT and interface as shown in Figure 2 on our company virtual interface facilitates seamless communication between TB and the DUT. We take advantage of UVM Compute DB to integrate the virtual interface into the UVM TB, which enhances the reusability and modularity of the test. The verification process includes waveform dumping and the simulation traceability and the execution of a comprehensive UVM-based test suite. Figure 2 is top-down SV. Figure 3 is include SVH. A header of Figure 3 is created consists of all preprocessor macros and conditional compilation directives to include different versions of the packaging file based on the LLM target and the iteration defined during a compilation. Only experiment with the LLM-based test generation revealed the various issues in the prompt and the balance between the split infrastructure instructions and the possibility of the LLM inference provided to be crucial. Omitting a comprehensive list of components of a phase of the UVM test which often led to an incomplete implementation, such as generating stimulus without a score for verification. Overly detailed prompt caused responses to truncate, highlighting the process limitation of the LLM with a certain prompting style. After extensive engineering effort, a general framework for the description of natural language was created, as shown in Figure 4. Please, Figure 4 is a verification description test simplified or outlined. Please set as a professional verification engineer. Value design of accumulated DUT is defined as the brief description of DUT functionality. DUT output interface. A queue interface is defined. Instance of the interface. The instance of the interface the virtual interface is set in the top module which wraps the DUT. Utilize the existing of the top module and refers to handle the signal interactions. Required. Brief description expected from each class, for example, the constructors and infinity phase and connect phase and run phase, and its transition class and sequence class and sequence subclass, drive class and monitor class, and agent class and scoreboard class and bottom class and test class, Make sure the connection between the sequencer, driver, monitor, and scoreboard are correctly established. Give me the complete code. B. LLM test bench generation. The benefit description text file is prompts the LLM to generate various components of a UVM test bench. The prompt include a brief description of the DUT behavior is used to guide the LLM to develop reference model of the DUT in scoreboard. I approach of the DUT, which is used to model transaction packet, UVM phase requirement, for example, build phase and count phase and run and etc. TL interface port and directionality. From the state of the art, the LLM listed in table 1, we selected 3, ChatGPT 4.0, Gemini 1.5, Pro, and Llama 3.2, and based on the consideration of the cost efficiency and computational resource constraint, all LLM runs were performed on the cloud using the chat-based feature, and all LLMs are run without memory, ensuring that a response on each iteration is independent and is not influenced by the previous iterations. C. The compilation build process. The LLM-generated TB along with the provided TB component interface tab is compiled using the Synopsys 2022.06. Upon the compilation failed due to the syntax error, an iterative correction cycle is initiated. During each iteration, prompt crafted to guide the LLM toward generating TB free of the syntax error, and the compilation process is repeated. Iteration refinement is arbitrarily kept at a fourth attempt. If syntax errors persist beyond 4 iterations, the process is deemed unsuccessful. Figure 5 is simulation coverage collection and linked report flow. D is simulation and coverage collection. Coverage collection is enabled during the build and simulation phases to collect coverage data, including line and condition toggles, finite state emotion, FSM branches, functionality coverage, cover group, and cover points. We include cover groups and a cover point in the interface shown in figure 6. Upon a successful field simulation process is initiated as shown in figure 5. If a simulation results in a runtime, it is indicated but excluded from the coverage analysis to maintain the accuracy of the result. Only data from a successful simulation runs are analyzed, allowing for the generation of the precise coverage report. The Unified Report Generator URG consolidated the coverage data from the multiple runs and produce HDM report for review. By merging data from the various simulation, a more comprehensive and insightful coverage analysis achieved. The interface SV, figure 6, and E is UVM linting. UVM linting is performed using Synopsys Euclid 2024-09, is identifying the coding the inconsistency usage violations in proper phase management to mitigate errors in complex verification component environment. This process, commonly known as code linting, plays a crucial role in ensuring the reliability and maintainability of verification code. By integrating the Euclid into verification workload, we gain a quantitative measure of the code quality, enabling evaluation of whether the generated TBs align with the industry standards and best practices. Rules are applied to a lint only on LLM-generated UVM code and not to the DUT interface or top. The clarity and simplicity, the account of the filter and the error, both representing critical errors, levels of the lint severity, are combined under a single category level error, which serves as a primary metric for analysis. This is reported along with one count with the count of warnings. The entire process from a build coverage collection is linting is automated through the use of makefiles. This approach improves workflow efficiency and simplifies the execution of tasks different LLMs, ensuring the consistent reproducible runs. And chapter 5, result and conclusion. Table 3 represents a consolidated result for 5 individual test runs that conducted of different DUTs for chapter 4, ChatGPT 4.0, Gemini 1.5 Pro, and Llama 3.2. The column build indicates the number of successful simulation builds following the LLM prompt refinement process to achieve the final result. For example, the entirety of 5 signified the LLM-generated UVM test to produce a successful simulation build on every attempt. Table 3 is syntax coverage and lint metric for a different design. The problems encountered during the development process mainly involved missing connect phase method in the UVM agent and environment, as well as incorrect use of the variable types within the UVM scoreboard, reading and build error. These problems were systematically addressed through the iterative debugging and careful examination of the code. Furthermore, the recurring source of the runtime errors was due to the improper handling of the TLM ports of the scoreboard, where mismatches between the expected and actual port types led to a functional inconsistency. Resolving these issues required defining the interface connections and ensuring the correct of the use of the TLM communication protocols. The coverage columns represent the coverage score reported by the Synopsys VCS, which is an average of all zero values of the line conditional towards FSM the branch coverage. Since zero values are excluded from the calculation, thus leveraging the method of the can obscures individual coverage metrics and potentially lead to a misleading interpretation. The lint column indicates the number of the count of the lint errors and a warning specify the LLM-generated UVM code and offering a quantitative measure of each quality. A is measure coverage metrics. A detailed analysis of the individual coverage metrics presented in Figure 7 is evaluating the ability to the LLM-generated UVM test bench to beyond the test bench correctness benchmarking with the test and achieving the functional closure. For each DUT, the figure that shows the minimum and maximum and average coverage achieved by the LLM across the 5 simulation builds. The Figure 7 is the coverage metric across all LLMs and DUTs. One is lint coverage achieved by the LLM-generated TB consistently outperformed the other metrics, frequently reaching full or nearly full coverage. This suggests that the LLMs can effectively generate a test bench capable of exercising the majority of the RTL. High line coverage highlights the LLM's strength in producing broad test scenarios that traverse most execution paths. 2. Conditional. The LLM-generated test bench shows a gap between the line and conditional coverage, emphasizing that while code execution is comprehensive, logical conditions may remain underexplored. For designs such as add_8-bit and adder_16-bit, conditional coverage is zero because the design do not contain the conditional logic. In benchmarking, it's important to note that null coverage for a metric may indicate the absence of the design feature rather than a failure of the test generated. For other designs, conditional coverage is relatively high in some cases, but in others, low coverage shows that the LLM select the contextual understanding to generate the test scenarios that adequately exercise a logical condition. Addressing these limitations could involve refining the LLM's prompt or integrating additional knowledge about the design structure to encourage more diverse to precise branching tests and using their constraint randomization or directed test cases. 3. Toggle. Toggle coverage for LLM-generated test benches closely aligns the line coverage, indicating the LLMs are effective in generating stimuli that exercise individual bits for designing. For example, designs such as ALU and adder, ALU and adder, and 16-bit achieves nearly as perfect toggle coverage, showcasing the LLM's ability to excite a low-level hardware mechanism. However, the pursuit result reveal a limit scope. LLMs excel in handling the straightforward exception paths but struggle with the more intricate logic testing. To expand the scope of the testing instead of the TV generation could aim to integrate a more nuanced, the higher level toggling, the target and cover and conditional of the FSM elements. For FSM, benchmarking indicate the FSM coverage made the most challenging metric for LLMs. FSM coverage is not applicable for a design that lack FSM feature. For example, ACCU and adder 8-bit and adder 16-bit. For design of FSM features, LLM-generated test benches struggle to create a targeted stimuli to exercise all possible test state transition. This shortfall highlighted the weakness in the current test bench generation approach, the lack of the mechanism to recognize the systematic exercise FSM. The future improvement could involve the increase in the understanding of the FSM structures and improving the ability of the LLMs to generate the state-specifically stimuli. 5 is branch. Branch is the coverage result reveal a pattern similar to a conditional coverage, where the LLM-generated test bench are unable to effectively explore some execution paths with branching logic. For example, ALU demonstrates a significant gap between the line coverage 96% and the branch coverage 79%, reflecting the difficulty in generating test cases and adequately evaluate all the branches of the design. This gap indicates the need for a better alignment between the LLM's output and the structural and the behavioral nuances of the design. Improving branch coverage would require more sophisticated test bench generation that identify and target the specific branches within the code. 6. Group coverage, which relies on manually edited cover points and cover groups and exhibit the high variability and either the 8-bit design and with only 0.18% and 0.820% of the beans covered on average. The bias sequences generated by the ChatGPT 4.0 and Gemini 1.5 Pro respectively. In contrast, 165 beans were created and at a 16-bit design, resulting in a average group coverage of 22.7% and 33.5% from the sequences generated by the Gemini 1.5 Pro and Llama 3.2 respectively. ChatGPT 4.0 achieved 39% group coverage of the ACECU design and significantly higher than its FSM coverage, but lower than its line coverage. The variability underscores the challenge for LLMs in the systematically addressing the manually defined beans. To improve group coverage, TB generation process should prioritize the incorporating the explicit knowledge of the cover point definition and intelligently targeting specific cover groups. Evaluating TBs based on solely the metric and such as group coverage highlighted the strengths and limitations of different generators in addressing nuanced, manually defined criteria. Assertion coverage is inherently tied to the presence of the assertion in the DUT, which are typically crafted by the designer to validate the specific conditions or behavior during the simulation. And the DUT evaluated the assertions were implemented and those benchmarking showed your personal assertion coverage in all test cases. Without assertion defined in the DUT or edited during the test bench generation, this metric becomes relevant for evaluation. B. LLM performance. ChatGPT 4.0 outperformed the other models in the most coverage metrics, demonstrating good lines, branch, and cover coverage. It achieved nearly perfect line coverage in most design, with the average reaching 100% for ACCU and FSM. ChatGPT 4 the ability to handle the complex scenarios such as FSM design with a high branch with a group coverage makes one of the most versatile and reliable LLMs to this comparison, often matching or exceeding the performance of the other models. 2. Gemini 1.5 Pro. Gemini shows a strong performance in specific areas, particularly to toggle coverage where it matches slightly scarce or slightly exceeded ChatGPT 4.0 for most designs. It also achieved the consistently line coverage and maintained 100% in simple designs such as a Q and either 8-bit, despite a slightly lower FSM branch coverage compared to the ChatGPT 4.0, and Gemini shows promises in the targeted scenarios, making a solid but perhaps less comprehensive option. With a usual input token size of 1 mega, Gemini 1.5 Pro excels and understanding the complex requirement of UVM test bench. Test bench consistent generated with minimal variability across the multiple runs, demonstrating the LLM's potential to achieve higher scores in the coverage benchmarked through the effective prompt engineering and iterative prompting. Gemini 1.5 Pro outperformed ChatGPT 4.0 by a small margin in overall coverage and ability to cover the benchmarking. 3. Llama 3.2. Llama is efficient in synthesis performance in all coverage metrics with a significant strength as the struggle coverage but a notable weakness in others, particularly FSM and group coverage. It achieves a perfect line coverage for a design like Adder 16-bit for filters with more complex scenarios such as FSM, which performance drops drastically. Its load branches and conditional coverage highlight the challenges in handling the intricate logic and decision-making scenarios, making it the local competitive to three LLMs in this evaluation. Llama 3.2 attempt to improve coverage metrics to incorporate constraint randomization into a transaction. However, this approach hindered the convergence of the build and ultimately lowering the overall coverage score. This result indicates a similar benchmark performance for Gemini 1.5 Pro and Gemini ChatGPT 4o. Llama 2.0 exhibition performance gaps in both build and convergence and functional coverage, indicating the need for further refinement to handle the complex scenarios effectively. The result do not reveal a clear correlation between the number of the model parameters on their performance on their metric evaluated. C. Challenges. 1. Functional correctness. During the multiple test runs, the LLM-generated score was frequently reported that the tests were failing, despite the fact that the DUT was fully verified, often due to the incorrect comparing of the interface object to the result in high impedance as the values in the scoreboard. This underscores the limitation of the LLMs in generating the scoreboard and actually model the complex state-dependent behavior of the DUTs, and these challenges highlight the need for specialized methodologies to improve the precision and reliability of the LLM-generated scoreboard in verification environments. Additionally, LLMs face difficulty in interpreting non-standard data formats in providing reliable error diagnostics and attending to the evolving DUT specifications, all of which are essential for effective verification. These limitations underscore the need for further refinement of LLMs in using specific model training to improve the accuracy and reliability of the LLM-based scoreboard to reflect the DUT behavior. The system research and SVA are the powerful tools for verifying the behavior of the design can be used for validate correctness of the model after the scoreboard by verifying the constraint and condition that must hold throughout the simulation. This ensures that the reference model is consistently checked against defined expectation, improving the reliability and accuracy of the scoreboard, including a detailed description of the DUT behavior significantly increase the number of the token processed by LLM, which can degrade the quality of the generated TB and to do the constraint of the current context windows limited. 2. Functional coverage. Coverage metrics such as FSM group coverage were very low across all designs. These highlight critical issues with the current sequence generation methodology. Currently, the TBs and the sequences generated by the LLM, which, while efficient in automating initial TB development, remained rudimentary in terms of test strategic sophistication, specifically lacks implementing of the constraint randomization does not include the directed test cases. Development aspect of the such restriction randomization directed test in the prompt can degrade the output quality, often resulting in the test errors and inconsistencies. This occur because the LLM, while the adapted pattern recognition of the basic code generation, struggle to meet the nuanced requirement of the complex test construction without introducing flaws. Any advent of the LLMs with large context windows could elevate both of these problems by enabling the model to handle extensive detailed input description without corresponding compromise in the output quality, thereby supporting the generation of more accurate and comprehensive test bench. Several efforts had been made to achieve the functional closure and sign off using the automated coverage-driven test adaptation, feedback loop, and artificial intelligence deep reinforcement learning. The achievement of the functional closure summarizes and the flow of the automation that is the generation of the test bench to functional sign-off proposed in this work. The conclusion. Benchmarks provide valuable information in the strength limitation of the UVM test bench generated by the LLM Through the detailed coverage analysis and performance evaluations, we learned that while the LLMs can produce efficient and comprehensive TP-term sums of line and toggle coverage, they struggle with the more complex aspects of such as FSM, branch and conditional coverage. These challenges underscore current limitation in the generation of sophisticated tester strategies, particularly when it comes to using the intricate design features and adapting the evolving DUT specification. The result emphasized the need for a few further refinement in LLM-based in the TB generation, especially in areas of constraint, randomization, and interactive test cases. The coverage gaps in the critical areas and highlighted the importance of improving the model's understanding the complex design behavior and specification beyond self-developed environment. Furthermore, the benchmarking process revealed that issues such as improper interface handling, incorrect variable types, and difficulties in TLM ports are recurring. The obstacles must be addressed to improve the reliability and precision of the LLM generated test bench. Ultimately, the finding of this test benchmarking effort stressed the importance of the careful integration and configuration of the TB component. Although the LLM shows the promises in the automating portion of the TB creation process, achieving full functional closure and sign-off requires more advanced methodology and deeper model training. Prompt engineering can address the core issues by improving the modularity and offering a flexible framework that supports human intervention, allowing the users to guide and refine the process, ensuring that the system reaches its desired functionality and performance with greater precision and adaptability. This benchmark as a result suggests that future LLM adjustment, particularly those with larger context windows and UVM-specific training, may mitigate the current limitation and lead to a more accurate, robust, and reliable verification solution. References like that, and okay, good. And then, good. Okay, we need today we read this paper, the VerifLLMBench, an open source benchmark for Testbenches generated with the large language models from DVCON2025. Thank you for your time. See you next time.